Okay, let's get started. Lecture 14 is about chapter 15 of the textbook, and this is the introduction of a new topic. This is the first time we start studying general equilibrium economies. After studying the dynamic optimizing behavior of individual agents like firms or consumers, it is time for us to start building economies, markets consisting of these agents. Sometimes we are interested in the dynamic behavior of individual agents, but sometimes we need to take this next step to build economies consisting of these agents, because for some problems it is inevitable to build general equilibrium economies. For instance, if we want to understand the effects of taxes in an economy, we cannot do this by studying the behavior of individual agents. To this end, we need a general equilibrium economy. There are two possible lines in building and solving general equilibrium economies. In the first line, we have no market distortions. This is the simpler case. In this case, we have the social planner approach, which is much simpler, because we can squeeze all the agents into a single Bellman equation. It is much simpler. To be more specific, we can write a single objective function on the basis, objective function on the basis of the objective functions of the individual agents. This is the approach we are going to study in this chapter and in the next one. In the second approach, there are market distortions, and this is what we are going to study in the last two chapters of the book. Okay, so now we are taking the first approach, which is based on the two welfare theorems. At the bottom line, these two welfare theorems, which are of fundamental importance in general equilibrium analysis, they are simple. They are quite simple. The first welfare theorem claims that a competitive equilibrium is always a Pareto-efficient allocation. This is just a kind reminder. A Pareto-efficient allocation is an allocation of resources in which no change can be made without making someone worse off. So this is what the first welfare theorem claims. And the second welfare theorem is the reverse of the first one. It says that any Pareto-efficient allocation can be sustained as a competitive equilibrium by an equilibrium price system. If we have a Pareto-efficient allocation, it can be a competitive equilibrium, supposing there is a price system which can be regarded as an equilibrium price system. And we need the details. We need to know the conditions under which we can have such a price system. And this is the task for today's lecture. This figure comes from the textbook. This is figure 15.1. This is about a single agent that tries to optimize on the consumption of leisure time and consumption. And we have two convex sets, set Y and set A. The lines in set A are the indifference curves, and set Y describes the technological possibilities. We know that the allocation L0 C0 is a Pareto efficient allocation, because this allocation is on the borderline of the technological possibilities. So we can know that the agent utilizes all the resources in a way, in an allocation. And in this point, the technological limit touches the highest possible indifference curve. So it is a Pareto-efficient allocation, and there is a line between the two sets, which can be regarded as a budget line. But you know, a budget line always defines a price system, a price ratio in this case. So there is a price system. In this case, there is a price system which can be regarded as an equilibrium price system. So in this case, this is just an informal, a quick demonstration. In this case, the Pareto-efficient allocation can be a competitive equilibrium because there is a price system that defines a line, a hyperplane in higher dimensions. It defines a line between the two convex sets. The convexity of the sets is no problem because both the technology and the preferences are concave. So the sets on the basis of the technology and on the basis of the preferences must be concave. What we are going to do is to clarify the conditions under which we can be sure that there is a price system. There is a hyperplane, in this case a line, that separates the two convex sets. So this is what we are going to do in turn. Let's go on with the dual spaces. Just a kind reminder, we are looking for price systems to a solution. But what is a solution to an economic problem, be it a dynamic or static problem? It is a sequence. For instance, in the case of the previous very simple static example, the solution was a two-dimension vector. In another case, when the problem is the basic, now classical growth model, its solution is an infinite sequence, which can be regarded, depending on the context, it can be regarded as the consumption stream or the sequence of the capital stock in distant periods. So we have a sequence as a solution, which can be finite, which can be infinite. So this solution has distinct dimensions, and the price system must fit these dimensions. So when we look for a solution to an economic problem, we always know the space in which we can look for the solution. For instance, to go back for a second to the previous simple example, we knew in advance that the solution is going to be a two-dimension point. So in this sense, there was no surprise. We know in advance the dimensions of the solution. So we have a commodity space, a normed vector space underlying each problem in which we are looking for the solutions. So any solution to a problem is a point in this commodity space, in this vector space. We can say point because any point in a space of with any dimensions, any point has coordinates, and the sequence which we interpret as the solution to the problem is exactly this order sequence of numbers. So this is a point, and the point has coordinates, and we emphasize the fact, the condition that we need the sequence as the solution, as a solution because in the solution numbers are ordered in a sequence. So in this sense, yes, in this sense, the solution is always a point. It's no big deal. What is more important is that the price system must fit the dimensions of this solution. So if we were looking for the solution to the previous problem in the space of two-dimension points, we also knew in advance that the price system was going to have two elements. So the price system was also a two-dimension vector. So in this sense, the point I want to make is that in this sense, the dimensions of the commodity space establish the dimensions of the price system. So the dimensions must fit. In general, if the k-dimension Euclidean space is the commodity space, then the price system is also going to be a k-dimension vector, and what is more important, it has the inner product representation. This inner product representation is the most important characteristic of the price system, because we can have a price system, we say we have a price system only if we have this inner product representation. This is the most important idea in this lecture. We can say that we have a price system only if we have such an inner product representation, because only if we have such an inner product representation, we have a price to each commodity in the solution. So we need this inner product representation. Price systems live in the dual space of the normed vector space we work with. So they are linear functionals. The commodity space is always a normed vector space, which is no big deal. This is a vector space because we are looking for a solution in points of a given space that we define on the basis of the details of the problem. And this is a normed vector space because there must be a norm on the basis of which we can measure the distance between points, by which we can measure convergence. So we need a norm. And the characteristics of this normed vector space establish the basic characteristics of the dual space, of the linear functionals which we want to interpret as price system. Some examples are very instructive. The textbook contains a couple one. Here I want to pick only one, because these are the spaces which we are going to use the most. For any finite p, LP is a normed vector space that consists of infinite sequences which are bounded in the appropriate norm. If P is infinite, then the space is L infinite, and its norm is based, it is a subnorm, so it consists of this space contains points which are sequences which has finite elements. Okay. The following equation is very helpful, because 1 over p plus 1 over q is 1 is an equation by which we can calculate q to any p, and q is going to q determines the dual space. So for any finite or infinite p, we can find LQ, which is going to be the dual space of the commodity space. So if we work with LP as the commodity space, its dual space is going to be LQ. The dual of L infinite is L1. So The most important aspect of this discussion is the fact that for any p, be it finite or infinite, a linear functional in LQ living in the appropriate dual space always has an inner product representation. And you may remember, we have just covered, this inner product representation is very important to us because this is the prerequisite for us to interpret a linear functional as an appropriate price system. So we need linear functionals that we can represent by inner products. But there is a problem, and this is a problem we will discover in detail very soon. There might be linear functionals on a normed vector space that don't lie in the related dual space. For instance, some linear functionals on L infinite are not in L1. So we can find, we will see very soon, on the basis of the two welfare theorems, we can find linear functionals on L infinity which we cannot interpret as price systems because they don't lie in L1. If they were in L1, we could interpret them as price system, but we cannot interpret them as price systems. We will see it soon. They cannot lie in the dual. So we need some tricks by which we can make sure that we will have linear functionals that we can interpret as price system. This is the task we are going to solve in turn. The first exercise for the day is exercise 15.3. Let's pick L infinity as the normed vector space we work with. In this space, we have infinite sequences that are bounded in this norm, in the subnorm, which means all the elements in any sequence in this space are finite. The claim is the dual of L infinity is L1. We need to show that any linear functional in L1 is a continuous linear functional which can be represented with the following inner product, which means that we have an inner product representation, which means this linear functional can be interpreted as a price system. What do we know about y? What do we know about this linear functional? We know that it is in L1. So given the fact that the linear functional is in L1, it is bounded in this norm. Okay, which can be written this way. Which is the same as this sum. And this sum is finite. So this is an infinite sequence which the elements of which give a bounded sum. So the sum is bounded. Okay, this is the point. What do we know about sequences in the space L infinity. What about the space, this space? This space consists of infinite sequences which are bounded in this norm, in the sup norm. So all the elements of a sequence are bounded. Elements are bounded. These are important details because what we are interested in is the inner product representation. We are interested in this inner product representation, and we need to make sure that the sum is well defined, because and it is well defined because both y and x are such that the elements in this sequence are well defined. So we have no infinite times infinite or infinite times zero type elements in this sum. So this is well defined. So the linear functional as an inner product representation is well defined. Some questions remained. We need to check if it is a linear functional. We need to check if it is bounded and if it is continuous, and if it is linear. So we need to check two characteristics: linearity. We have x and z, two infinite sequences in L infinity, and we have two real numbers. So let's see what happens. Let's put this weighted sum into the linear functional to check if it is linear. It's no big deal. So it stands in the place of x in the sum, and here we can use the linearity of y. We know this is linear. This is not zn, this is xn. My mistake. Yep. I think it's correct now. So finally we have this result. So it is linear. We need to check if this linear function is bounded and continuous. The two conditions are the same. So if a linear functional, please check the definition on page 445. If a linear functional is bounded, it is continuous, and if it is continuous, it is bounded. This is theorem 15.1. Let's use Hölder's inequality. So this is the linear functional, and this is the same linear functional after expansion. Of course, this inequality holds. Which can be summarized this way. This is an infinite sum. Okay, and this is Herder's inequality, because this inequality must hold. Oh geez. And it is finite. Okay, because both sequences, the norms of both sequences are finite. So finally, we have two results. On the basis of the Herder inequality, we have this inequality. And by the definition on page 445, it is also true. And the two inequalities are very similar. But please note that of all the possible numbers to which this inequality holds, this is the smallest number. So the norm of the linear functional. So this is the consequence that this inequality holds. So the linear functional is bounded, hence it is continuous. So yes, we have continuous and bounded and linear functional in space L1. The following exercise is exercise 15.4. We have a new space as a norm vector space. The candidate for a norm vector space, this is C0, which is a subspace of L infinity. So space C0 consists of infinite sequences which lie in L infinity, but which converge to 0. And first of all, we need to check if it is a normed vector space. If C0 is a normed vector space, to show this, we need to check is a normed vector space. We can show this by the use of the definition on page 43. We need to check if the operations follow the simple algebraic laws, and it's no big deal. So it is easy to see that all characteristics from A to H, they are satisfied. So C0 is a normed vector space. So it is a normed vector space, and C0 is a subspace of L infinity. So the norm of the vector space L0 is naturally a norm for C0. So C0's norm is the norm of the vector space L0. We need to check if the dual space of C0 is L1, the same as the dual of L infinity is L1. We need to check two things. First, if we have a bounded continuous linear functional on the subspace C0, we need to check if its inner product representation lies in L1. This is the first thing to check. And second, we need to check if we have a sequence, the inner product representation lying in L1. We need to check if it defines a bounded and continuous linear functional. So the first, we have a linear functional that has a sequence representation in this form, and we need to see that that the sequence y is bounded in this norm, because this is the norm of the space L1 in which the linear functional is supposed to lie. Let's define the following numbers. Cn is 1 if phi en is strictly positive, and -1 if xi en is below 0. And from this, let's define a sequence. Let's define this sequence on the basis of the xi numbers, and most importantly, after the nth element in this sequence, we have O0. Okay, so to any n, capital N, Zn is an infinite sequence that lies in C0, and we need to see what happens to the linear functional phi if we put Zn, the sequence Zn, into the linear functional. So let's try to see what happens. Okay, we have this inner product representation, and we need to check if it is in. Okay, let me show. So we need to check if this sequence lies in L1. It is equal to this sum, and it is equal to this sum. We are just using our own definitions. And now we can use the numbers Cn okay, and now we use the fact that Cn is 1 or -1. This is the one fact we use, and we use the other fact that after Cn we have zeros. So these are the two facts which we are going to use. So it equals to this sum. Please note it comes from this fact, and it comes from the fact that xi is 1 or -1, so in absolute value this equality holds. Okay. And it is also true, so here let me highlight the two ends of this system of equalities. So this is the point we want to use later, and it is also true because of the continuity of the linear functional. So this is finite. This is supposed to be finite because we use this norm in this space, and this is 1. So this is the explanation to this inequality. All right. And so this is 2. And we also know that this is finite because of phi is a bounded continuous linear functional. So at the end of the day, we have this inequality. Phi times the norm of Zn in this norm, which is phi, which is finite. And please note that this is the norm of the sequence in this norm. Okay, so y is bounded. Result, y is bounded in this norm. It comes from this fact. Okay, so bounded in this norm, so in consequence y lies in L1. And it is also true even if n goes to infinity. Okay, this is the first thing we needed to check, and the second thing we need to check is if y lies in L1, then we need to check if it defines a continuous and bounded linear functional phi. Okay, we have this representation for the linear functional. From this, it follows okay, and from the Hölder inequality,
So this is what we have just established, and it comes from Herder's inequality, just like in the previous exercise, from which it follows that phi cannot be higher than the norm of y, which is finite, because this is finite. So the norm of phi is bounded, it is finite, so phi is bounded and continuous, as this is what we wanted to demonstrate.
In the two previous exercises, we studied the connections between commodity spaces and their dual spaces, but we are still interested. We did this with a purpose, because we are still interested in finding price systems to solutions to economic problems. We saw in the introduction that that a Pareto-efficient allocation can be regarded as a competitive equilibrium only if there is a price system that generates a hyperplane that separates the two convex sets. This is a very simple idea which can be represented in a simple figure, but we can state the same idea in general in the Hahn-Banach theorem, which is theorem 15.2. If S is a normed vector space, and if A and B are subsets of this normed vector space being convex sets, and in the case where S is infinite dimensional and when B has an interior point, the intersection of A and the interior of B is empty, or in the other case, when S is finite dimensional, the intersection of the two sets are empty. So in these cases, there is a non-zero linear functional that separates these two sets. It seems to be simple, but the condition that set B must have an interior point is problematic. We will see that it's not difficult at all to find a normed vector space that seems to be appropriate. That seems to be a good choice for a commodity space, but by the fact that the space has no interior point, it makes it inappropriate. Let's have an example. There is an example on page 451, and it is very exciting. Let's have S as the space of infinite sequences bounded in the following norm, and let's have the infinite dimension unit ball around the 0 point. Let's have the 0 point, and in exercise 15.6 we can see that the 0 point is not an interior point, because okay, we will see it in detail very soon. We can always find points in the neighborhood of the 0 point that lie outside the unit ball of the space, and later we will use the fact that the positive orthant of the space with this norm has no interior point at all. So this condition that any convex set B must have an interior point is problematic, because it's not too difficult to demonstrate that the positive orthant of the space consisting of points that are bounded in the norm, the space has no interior points at all. On this ground, we turn to the welfare theorems. They are theorem 15.3 and 15.4. A competitive equilibrium, including a price system, implies a Pareto optimal allocation. This is the simpler of the two. And the second welfare theorem claims that under assumptions 15.1 up to 5, there is a price system to a Pareto optimal allocation, which, if it satisfies the conditions of the remark related to the second welfare theorem, it is a competitive equilibrium. So I think it's important, it's an important condition, that the second welfare theorem in itself doesn't guarantee the existence of a competitive equilibrium. The second welfare theorem only ensures that we can find a candidate price system that must satisfy the remark, this is a related theorem to the second welfare theorem, and if there is a price system on the basis of the second welfare theorem which satisfies the remark related to the second welfare theorem, then it is a competitive equilibrium with an appropriate price system. We skip the demonstrations of the theorem, so we can go on with some important and exciting implications of the theorems.
The next exercise is 15.6, which is very important because it has some key implications regarding the interiors of sets and spaces. We need to check if there is an interior point in a set. So let's have S as a space of infinite sequences which are bounded in this norm. This is going to be a quick exercise, but very important, as I have just emphasized. So we have infinite sequences which are bounded in this norm, and we have a set, a convex set in this space, which is defined in this way. Simply put, it is the unit ball in the space of infinite sequences. Okay. So set B consists of infinite sequences which lie in S, but the elements of which are not greater than 1. Let's have a point. Let's have a point in S. This is theta 0 sequence. If we could imagine a space of infinite dimensions, then point theta would be its origin in the coordinate system that represents this space. So this point lies in the middle of the coordinate system, and it also lies in the middle of this set. Okay, this is the unit ball around the origin, and this is the point theta is the origin. We want to show that theta is not an interior point of B. How should we do that? If a point is an interior point of a set, then there is a neighborhood, a ball around this point that still lies in the set. So if theta is in the interior of set B, then we have a neighborhood, an epsilon neighborhood around theta, so that this neighborhood to this non-negative epsilon is a subset of B. Let's have an infinite sequence which consists of zeros with one exception in the t's position, this is epsilon over beta at t minus 1. So this point lies very close to theta because there is only one element in which we can find a difference. Okay, so the first question to check if yt is the element, whether it is in the epsilon neighborhood around theta. We can judge it, we can decide it on the basis of the norm. So let's actually this is what we want to calculate, but theta consists of zeros, so we are calculating the distance between the 2 points, but theta is all 0, so we can disregard these elements, and yt is also all 0 except at one place in the t's position, and this is beta times epsilon, which is lower than epsilon. So yes, the norm of point yt is b times epsilon, which is lower than epsilon. So in consequence, we can say that yt is in the epsilon neighborhood around theta. The second question. To check if yt is in B, is in set B. Because this is the condition we need to say, to claim that theta is an interior point. Any point is in B, any point is in B, set B, if for any t it's in absolute value it is not greater than 1. The sequence, the yt sequence, 10th element is the 10th element of the sequence yt is described in this way, which can be greater than 1 to any epsilon, and this is the point. No matter how small epsilon is, we can find an appropriate beta and an appropriate t to which epsilon is greater than this very, very, very small number. So to any epsilon, this element of yt is greater than 1. So, in consequence, yt is not in B. Hence, theta is not an interior point of set B. This exercise, we will get back to this exercise later when we want to show that the positive orthant of some spaces have no interior points at all.
With the two welfare theorems, we know the conditions under which a Pareto-efficient allocation can be a competitive equilibrium. There is an important point here. As I have mentioned, the second welfare theorem and the remark claims that there is a linear functional that can be a competitive equilibrium, the component of the competitive equilibrium, but these three theorems together cannot ensure that the appropriate linear functional has an inner product representation. So there is no guarantee that the linear functional that satisfies the conditions of the theorems actually has an inner product representation, so it can be regarded as a price system. So, in other words, even if we have a linear functional on the basis of the two welfare theorems and the remark, there is no guarantee that there is a price system. And we want a guarantee, so we need linear functionals that can be interpreted as price systems. Here we want to focus on the norms, because please remember the commodity spaces are normed vector spaces, and the norms that we use as norms are important in many respects. For instance, it depends on the norm if a utility function is continuous, and you can remember that assumption 15.3 that establishes the continuity of the utility function as a prerequisite for the second welfare theorem. The norm is important in this respect, because the continuity of the utility function depends on the norm we choose, and the continuity of the utility function is a prerequisite for a competitive equilibrium under theorem 15.4. And it also depends on the norm if the set has an interior point, which is related to assumption 15.5. And the norm also determines the class of continuous linear functionals, because continuity is always with respect to the norm. So a lot depends on the norm of the norm vector space that we use as a commodity space. As an instructive example, let's turn to page 459. We have a one sector model of optimal growth. An allocation in this example is an infinite sequence, so we need a space of infinite sequences. But what space should we pick? Any space LP is useless, because these sequences are supposed to be bounded in the norm by which they must be convergent to the zero. And if we chose this space as the commodity space, we would limit ourselves to solutions that are convergent to zero in the far end. And we can choose this space, norm vector space, as a commodity space. By choosing this space as the commodity space, we would limit ourselves to solutions which are convergent to zero, and we cannot be sure that such solutions converging to zero in the far end are the best possible solutions. So we may find other commodity spaces that don't constrain sequences to be convergent to zero, that may be better solutions. Okay, so we need another space. For any finite p, it is another problem. For any finite p, the positive orthant of the space LP has no interior points. So in this case, we couldn't rely on the working of the second welfare theorem. So for these reasons, for any finite p, the space LP is not a good choice for the commodity space. However, L infinity as the commodity space seems to be a good choice for the commodity space.